I'm one of her PhD students here in Berkeley. And today we're going to be talking about the correlation in ground motion duration and the effects we can see in a bridge that we chose for a case study. And as collaborators, we have Jenny Watson and Camila, who is going to be presenting the ground motion correlation part. Camila, do you want to say anything for your introduction?
Yeah. Oh, you hit it all.
Okay. Yeah, so Camila is going to jump into the hazard analysis and walk you through that. Camila, let me know when you want me to switch over the slides and everything.
Perfect. That sounds good. Go ahead and go to the first one of my slides. You can go to the next one.
Okay.
Perfect. So like Camila said, my name is Michaela Largent. I work with Jenny Watson Lamprey at Slate Geotechnical Consultants. Our portion of this project was to actually calculate the correlation between spectral duration and spectral acceleration. To do this, we took the intra-event residuals from 4 of the NGAOS2 ground motion prediction equations, along with residuals from 3 duration prediction equations listed here. I want to give specific thanks to Yusuf Bezorgnia, Norm Abrahamson, and Jonathan Stewart for providing different components so that we could actually do this analysis. So with these different residuals, we use the equation, the large equation at the bottom of this slide, to calculate the correlation coefficient. In this equation, n is just the number of samples, so number of ground motions that we looked at in the NGAOS2 database. X is the intra-event residual from the GMPE, and Y is the residual from the duration model. So then you can see our results in the next slide, Camila. Of the correlation coefficient. So this is comparing the Abrahamson et al. 2014 GMPE with the 3 duration models listed in the previous slide. And you can see that there is a large correlation, specifically in shorter periods. There seems to be a stronger correlation with the 575 duration rather than the 595 duration. Specifically looking at the bottom graph, there seems to be a stronger correlation with the Afshari and Stewart 2016 model compared to the other 2 duration models. This is likely because we actually were given the intra-event residuals for the duration model rather than just calculating them within this study. So we use these correlations in the next couple steps, but first in the next slide, we walk through the hazard analysis. So we performed a seismic hazard analysis for the Coronado Bridge and specifically concentrate on the 2475 return period. So that top uniform hazard spectrum in the gray, and also deaggregated the results so that we could find the mean magnitude and distance, which ended up being magnitude 7 at around 1 kilometer because the Rose Canyon fault pretty much goes right under the bridge. So using these seismic hazard analyses, we can then start to look at the actual correlation of duration to spectral acceleration in the next slide. So this just walks us through all of the steps pretty briefly, and then I'll go into more detail in the next 2 slides. So we take that 2475-year spectrum and we scaled it with factors of 1 to 4.5. Then for each one of those spectrum, we find the epsilon value at 1.5 seconds, which was around the period of the bridge. We calculate the mean duration using that deterministic scenario that I listed in the last slide, so the magnitude 7 at 1 kilometer. And that kind of gives us all of the components for this equation to calculate our new mean duration, about this correlated mean, basically. And then we select time histories based off of this correlated mean rather than just the mean duration like we would typically do for a seismic analysis. So you can go to the next slide. So in this one, we're showing how we're calculating the epsilon. So in the blue line is our median, so that magnitude 7 at 1 kilometer. And then the red line is our 2475 with a scale factor of 1, and the green is with a scale factor of 4.5. So then we calculate that epsilon just based off of how many standard deviations away from that blue line are we, and that gives us one component of that last part of that equation. And then in the next slide, it all comes together. And this is my last slide, and then I'll pass it off to Camila. So we have the mean duration, which we just calculate this based off of the deterministic scenario and the duration models. The sigma comes from the duration models. I think we're using the Abrahamson and Silva sigma here. The correlation was calculated using all of the ground motion database that we had in the residuals. And then each one of those epsilons gives us that last component, and we can calculate the correlated duration. So you can see that it starts to change pretty drastically. So the mean duration originally calculated for the 595 was 12.8 seconds. And then when we scale the 2475 by a 4.5 scale factor, we get a duration of 11.2 seconds. So we selected different time histories than that original mean duration. So Camila was given 7 suites of 11 time histories to then go and develop her fragility curves. So I'll go ahead and pass that off to you, Camila.
Yeah, thank you, Michaela. Basically, as Michaela was saying, as we increase the intensity of the earthquakes, we can see a decrease in the duration of the ground motion. So for the structural analysis specifically, we were expecting to see a reduced damage as we start to use these correlations. So first, I'll talk to you about our structural analysis. So for this, we developed a numerical model using OpenSeas of a major toll bridge. Specifically for this case, we chose the Coronado Bridge because it has very flexible piers and is partially isolated over a portion of the span. For the model, we had lead rubber bearings, which we modeled using the Book 1 model in OpenSeas. We had linear elastic beam columns for the girders and a very simplified boundary conditions for the abutment and the foundations, because our focus was really the piers, how the piers are damaging throughout, because this is what we're going to use to sort of use a damage measure later on. So for these, we use beam with hinges, and we use concrete O2 and steel O2 to capture that degradation after each cycle. And also, as you can see in like the top view, there is the bridge has a nearly 90-degree bend in the span, which contributes to asymmetry. So we also use bidirectional ground motions in the analysis. So for the damage analysis, we looked into Caltrans and Saini and Sandy 2014 study, which is referenced in Caltrans, to come up with drift thresholds for damage states of the piers. Specifically today, I will be showing you damage state 3 and damage state 5, which are the major and moderate damage levels. And these are the ones that Caltrans typically uses to label bridges. For the bearing, we chose a single damage state, which is damage state 5 as a major damage level, and it's 235% because this is where we predict the buckling limit will reach when we use the overlapping area of the bridge. So for the analysis results, I'll be showing you specifically Pier 14, but we came up with fragility curves for for all of the piers in the bridge and all of the bearings. For ease of showing you the graphs, I'm just showing you one because this is mostly the controlling case, as it is the most flexible pier that has an isolator on top. So for Pier 14, and this is the non-correlated with the non-correlated ground motions. So you can see damage state 5 and damage state 3 for these pier, and the distribution for all the other piers is very similar to this one. They're just shifted to the right. For the bearing, you can see this one was easier to show you since we have a single damage state. You can see the distribution of all the bearings on top of Pier 2 to 14. And as you can see, Pier 14, which is the purple one, has mostly controls when it's above the median. Below the median, we see some of the other piers starting to control, but it's very few, so we're still showing you mostly Pier 14. For the overall bridge, in order to come up with the damage states, for damage state 3, it's really controlled as the maximum of all the piers in the bridge. And for damage state 5, it's whether it's maximum between the piers and the bearings damage states. So for the results comparison, I'll show you the same curves, but as we took them from the results from the correlated ground motions. And again, for Pier 14, in the dotted line, you can see the non-correlated results, and in the solid line, you can see the correlated results for both. So here, as we expected, we see a shift in the fragility curves. And above the median, we see that there is a reduced probability of collapse. And this happens also in the bearings. Here I chose 3 representative bearings, peer 3, 5, and 14. And you can see this shift in the peer. We see also, I don't know if this pointer will work, but at the bottom, there is some, below the median, there is some cases where the correlated ground motion starts to control. And that we find that that's something interesting, like we didn't expect that, and that's something we'll want to look into the future. So for the overall bridge, this is what those fragility curves look like. And as I was mentioning, for DS5, you can see a very clear shift in the fragility curve, and it looks pretty nice. And then for 14, for damage state 3, you see a little bit of that lower part, but in the median, you really see that there is a shift in the damage probability is lower when you have that correlation. So in conclusion, if we don't account for this correlation, we might be overpredicting the durations, as Michaela said. And also, when we account for the ground motion correlation in the analysis, we see that the median damage level occurs at larger intensity values. For future work, I would like to add, to complete the peer PV framework, I would like to add the loss of analysis. And also, we are planning to repeat the analysis for a typical highway overpass that's smaller than the Coronado Bridge, and see how those results might come up and compare. And also, we're using the same model that I used for this presentation for the Coronado Bridge to do a hybrid simulation test with a lead rubber bearing. We're testing in the lab, and we're specifically looking at the rotational behavior and using the data for updating the numerical model of all the other bearings and look that into the analysis. And with that, I'll take any questions you might have. Thank you. Do you have any questions? Yeah, let's go there.
Thank you. When you said that correlated and non-correlated, it's just a duration bucket.
Yeah.
And then the non-correlated is you actually positive duration bucket, but it's not consideration.
So in the, Michaela, can you hear? Yeah.
So let's repeat it. The question.
Yeah, Michaela. So the question was basically what's the difference between the correlated and non-correlated, specifically when you're doing the ground motion selection?
Yes. So the biggest difference is that we're selecting time histories according to those duration values. So like in the slide that I showed, where it was 12.8 versus 11.2, we would be trying to get ground motions within the 12.8 second range rather than the 11 point. And obviously it's a range, it's never perfect. But it does, as you can see with Camila's results, it does change the answer. It's just our ground motion selection process.